system of the heart. Components. The conducting system of the heart is made up of specialized cardiac muscle fibers, and it is responsible for initiation and conduction of cardiac impulse. The conducting system of the heart consists of the following 5 components: the sinoatrial node, atrioventricular node, atrioventricular bundle, right and left branches of the bundle of his, subendocardial Purkinje fibers. Sinoatrial node. Sinoatrial node is also known as node of Kith-Black. It is a small horseshoe-shaped mass having specialized myocardial fibers situated in the wall of the right atrium in the upper part of the sulcus terminalis, just below the opening of the superior vena cava. It is known as pacemaker of the heart because it is generate impulse about 70 per minute and initiates contraction of cardiac muscle, producing a heartbeat. Atrial ventricular node is also known as node of Tora. It is smaller than the SA node and it is located at the lower part of the atrial septum, just above the attachment of the septal cusp of the tricuspid valves or opening of the coronary sinus. It conducts the cardiac impulse to the ventricle by the atrioventricular bundle. The AV node is capable of generating impulses at the rate of about 60 per minute. The speed of conduction of cardiac impulse, which is about 0.11 seconds, provides sufficient time to the atria to empty their blood into the ventricle before ventricles start contracting. Atrial ventricular bundle of it begins from the AV node and crosses the AV ring and runs along the inferior part of the membranous part of the interventricular septum, where it divides into the left and the right branches. Since the skeleton, which is fibrous framework of the heart, separates muscles of the atria from the muscles of the ventricles, the bundle of is the only means of conducting impulses from the atria to the ventricles. Right and left branches of bundle of the his. The right branches passes down to the right side of the atrioventricular septum and then subendocardial on the right side of the septum. A large part of it continues in the septum marginal through baculum to reach the anterior papillary muscle and anterior wall of the ventricle. Its Purkinje fibers then spread out beneath the endocardium. The left branch descends on the left side of the ventricular septum, divides into Purkinje fibers which are distributed to the septum left ventricle. Purkinje fibers. They are the terminal branches of the right and the left branches of the bundle of his and spread subendocardial over the septum and the rest of the ventricular wall. The conducting system and the mode of contraction of cardiac muscle is summarized as follows. The SA node initiates an impulse which rapidly spreads to the muscle fibers of the atria, making them to contract. The AV node picks up the cardiac impulse from the atria and conducts it through the AV bundle and its branches to the papillary muscles and walls of the ventricles. The papillary muscles contract first to tighten the chordae tendineae, and then the contraction of the ventricular muscles occurs. Arterial supply of the conducting system of the the whole of the conducting system of the heart is supplied by the right coronary artery, except a part of the left branch of the AV bundle which is supplied by the left coronary artery. Clinical correlation. Conducting system defects. The defect of damage of conducting system causes cardiac arrhythmias. The SA node is the spontaneous source of generation of cardiac impulse. The AV node picks up these impulse from atria and sends them through the ventricles through the AV bundle, the only means through which impulses can spread from the atria to ventricles. If the AV bundle fails to conduct the normal impulses, there is alteration and the rhythmic contraction of the ventricle, which is known as the arrhythmias. If the complete bundle of blocks dissociation in the rate of contraction of atria and ventricle, the commonest cause of the defective conduction through AV coronary arteries. An important point to be noted here is that rapid pulse is called tachycardia. The slow pulse is called bradycardia, and whereas irregular pulse is known as rhythmia. So it is very similar to skeletal muscle contraction with a few differences. Unlike skeletal muscle, the impulse that tells the cardiac muscle to contract doesn't come from the nerve. It comes from the pacemaker of the heart. That's the sinoatrial node. I have already told about their conducting system that generates an action potential. The action potential is in the contractile cells is different than how it was in skeletal muscle. So there is a plateau during which calcium enters the cell, and that is through a voltage gated L-type calcium channel on the membrane of the T tubules. So calcium ions move along their gradient entering the sarcoplasm. So in the intracellular calcium contraction rises, but the calcium is insufficient to cause contraction on its own. What it does is it also triggers a calcium release channel. On the surface of the sarcoplasmic reticulum, this is calcium induced calcium release. So the calcium rising inside the cell has two sources, the extracellular fluid and the sarcoplasmic reticulum. And the next series of the steps in the same, calcium binds to troponin C, and ultimately by the thin filament sliding over the thick filament, the sarcomere shortens and the muscle contracts. At the end of the plateau, the calcium influx is going to stop. Now what happens to the calcium? The inside cell calcium, the ions get pumped out of the sarcoplasm back into the cytoplasmic reticulum and out into the extracellular space. The sarcoplasmic reticulum has a calcium ATPase pump that uses ATP and moves calcium against its gradient back inside the sarcoplasmic reticulum. This is the sarcoplasmic endoplasmic reticulum, calcium ATPase type 2. The sarcoplasmic membrane, which is basically the plasma membrane of the cell, has a sodium-calcium exchanger. This moves sodium along its gradient, so sodium would enter the cell in exchange for calcium leaving the cell. So you can see how calcium gets out of the cell through the exchanger. That sodium is then going to be pumped out by the sodium-potassium ATPase pump. So the calcium level in the cell becomes back down again, and when another action potential arrives, the process repeats. The tension that develops in the myocardial cells depends on the intracellular calcium concentration. The ability of the myocardial cells to contract and generate force is contractility. If there's increased calcium influx through the L-type calcium channels, there's going to be more intracellular calcium. So there's increased contractility. If there's increased calcium uptake into the sarcoplasmic reticulum, then there's going to be more calcium being stored, which can get released during the next contraction, again increasing contractility. This can happen with phosphorylation of these channels, which sympathetic stimulation does. Remember, the heart is supplied by the autonomic nerves, the sympathetic and the parasympathetic nervous system. Sympathetic stimulation can increase contractility, so they are said to have a positive inotropic effect. Inotropism is the term that's used for contractility. So more contractility means its positive inotropic effect. While the parasympathetic system has the opposite effect, it has a negative inotropic effect. It reduces contractility more so in the atria than in the ventricles because they innervate the atria more. So like this, there are other factors which can either increase or decrease cardiac contractility. And this contractility together with period and afterload are important factors that determine the stroke volume of the heart and thus the cardiac output.